think I should give people bonus points for reminding me to record. Okay, so we are on lecture 24 notes. And we talked about confidence intervals for a proportion, the margin of error. We did this problem already in this one here. All right, so we are going to talk about estimating sample size. In these kinds of situations, we want our margin of error to be no bigger than a certain amount, like 1% or 2% or 5% or whatever that number is that's important to you. And before we do our study, we need to determine a sample size to obtain this margin of error. If you construct a confidence interval for a proportion and its width is 50%, that's no good, it's useless. So you want to make sure that you don't waste time and money on doing a study if the information you're going to get is so imprecise that it's unusable. This is especially true if you're going to be studying something where you have to use test animals, if you have to kill some mice because maybe you're doing like a study on cancer, then you want to use as few mice as possible to get your required margin of error. So here's my example. We want to predict the percent of people voting for Trump to within a margin of error of 1%. We're going to construct a 95 confidence interval, and we need to know what should our sample size be to achieve this level of precision. Remember from last time, the equation for margin of error is your z critical value multiplied by p hat times 1 minus p hat divided by your sample size. We know the margin of error, so we can replace that with 1% as a decimal. This is a 95% confidence interval for a proportion, so our z critical value is 1.96. We don't know p hat because we haven't taken the sample set, and the thing we're trying to solve for is n. So this is our problem. We don't know p hat until we take our sample. So what value can we use for p hat? Well, these questions are nice because the worst case scenario happens when p hat equals 0.5. So when you're doing sample size calculations to be on the safe side, we're going to assume a worst case scenario and always replace the p hat with 0.5. This will give you the maximum sample size you'll need to actually guarantee your margin of error will be that 1% or smaller that we're looking for. So I'm going to do this problem on the whiteboard. So we had our margin of error, 0.01, is equal to 1.96 multiplied by the square root of, replace p hat of 0.5, multiply that by 1 minus p hat, and divide by the sample size, which we don't know, n. So we're trying to solve for n. This piece here, 0.5, this is just 0.5 times 0.5, which gives you 0.25. So we get 0.01 is equal to 1.96 multiplied by the square root of 0.25 over n. So we can divide both sides by 1.96. And to get rid of the square root, we can undo that by taking or by squaring both sides. So we have 0.01 divided by 1.96 squared is equal to 0.25 over n. So let's go ahead and figure what this side is. We'll do some rounding. 0.01 divided by 1.96. Take that quantity and square it. And you get too small of a number. So let's see. Let's do this. So on this side, we have 0.01 divided by 1.96, and this whole quantity is squared. And really, it's over 1. Let's see. I want to do it this way. Sorry, I changed my mind. All right, each side of the this side of the equation is being divided by n, so we're going to multiply both sides by n. So we get 0.01 over 1.96 quantity squared times n is equal to 0.25. And these guys are just being multiplied together, so undoing the multiplication, we can use division. So we get this, n is equal to 0.25 divided by 0.01 over 1.96, that whole quantity squared. This whole thing is in the denominator. I'm going to put brackets around it to emphasize that this whole piece is in the denominator. So if you do that calculation, if you put everything into your calculator at once, you get that this side is 9,604. If you ever get a decimal number, you're always going to want to round up. That way you'll be in your margin of error for sure. This is a huge sample. So any type of poll that you see on the internet, they're never going to have a margin of error of 1% because you need almost 10,000 people in your sample to get that margin of error. Questions about this? This is an important question. It comes up a lot. So we could also write this down in a simplified format so that you don't have to go through these algebra steps each time. Note, to get n, choose the smallest whole number that is larger than So think about what we have here. It's the margin of error divided by the z critical value, and 0.25 will always be in the numerator. This is the same thing as dividing by a fraction, so you could also write it this way. That is bigger than 0.25. So let me put a parentheses around it to show that this is in the numerator, 0.25 multiplied by your z value squared divided by your margin of error squared. So you should get the same thing that we did above using that formula as well. So we could do 0.25 times 1.96 squared divided by 0.01, and you get the same thing. Oh, sorry, 0.01 squared, and you'll get the same thing. Questions about this? All right, we'll go back to the notes. Anytime you construct a hypothesis test, it's really the same thing as doing a two-sided, or anytime you construct a confidence interval, it's really the same thing as doing a two-sided hypothesis test. So constructing an 80% confidence interval is equivalent to doing a two-sided hypothesis test at the 1 minus alpha significance level. So a 95% confidence interval is equivalent to doing a 5% significance test for your hypothesis test. A confidence interval represents all the plausible values of that parameter. So if your hypothesized value is in the confidence interval, that means you're going to fail to reject H0 because it's a plausible value. And if your hypothesized value is not in the confidence interval, you're going to reject H0. This works for all confidence intervals, not just proportions. So this shouldn't say works for all means, not just proportions. We should really change this to all confidence intervals. Two-sided. So here's an example. We'll go back to, see, which one did we do? I feel like so we did one yesterday about the proportion of people who spend more than $500 or less than $300 on books. So we can go back to that example. Or we could do the one for the polling data that we did in Arizona. So I'm going to go back to the polling data one. And we had, it's predicted that Biden will get 52% of the vote, and I think our sample size was something like 600. And our margin of error is already given to us, so we can actually just construct the confidence interval for that. The 95% confidence interval for the proportion of likely Arizona voters who will vote for Biden is 0.48 to 0.56. So here's a hypothesis test we could do. We'll say this is at the 5% significance level, since this 5% and the 95% have to add up to 1. At the 5% significance level. We'll say that our H naught is that P is equal to 0.53, and that our alternative here is that P is not equal, because it has to be two-sided, 0.53. In this case, based on our confidence interval, would we reject or fail to reject?
Fail to reject.
Failed to reject. We would fail to reject since P equals 0.53 is in the 95% confidence interval. And here is test 2. We'll say H naught here is still a 5% significance level, is P equals 0.6, or yeah, we'll just say P is 0.6, and HA alternative is that P is not 0.6. So we look at our confidence interval and 0.6 is not in there. So that means we are going to reject H naught. Since 0.6 is not in the confidence interval. So some teachers, they don't teach hypothesis testing at all. They just teach confidence intervals, and then you can do a hypothesis test this way. The problem is you can only do two-sided hypothesis test when you have a confidence interval. Questions about this?
Where did the 0.6 and 0.53 come from?
I made them up.
Okay, cool.
So you'll get something, you'll probably get a multiple choice question like this on the final exam. And that's all you really need to do. Check if these numbers, if your number for H naught is actually in that interval or not. And that's it.
On the final, are we gonna have more multiple choice?
Yeah, you're definitely going to have more multiple choice on the final because of the fact that I have 48 hours to grade those. Each exam for like right now takes me about 10 minutes to grade. So I'm doing like 11 to 20 hours of exam grading that I'm not going to be able to do in 48 hours. So yeah, so it'll be more multiple choice. I don't think I'll look for a lot of partial credit since I just don't have time.
Is it from like the beginning of the semester also?
Yeah, it's from the beginning of the semester. I try to make it equally weighted. So test 1 material will be about 25%, test 2, 25, test 3, 25, and then new stuff up to 25%. But there's a lot of overlap with this new stuff and the last exam stuff because it's still confidence tests, confidence intervals and hypothesis. Well, I guess we didn't have confidence intervals yet, but there's still hypothesis testing. So instead of asking you to do a hypothesis test with a mean, I might ask you to do one with a proportion.
Wait, in this last case, why was the probability 0.6 not within?
Okay. So if we go back to looking at that confidence interval, our confidence interval goes from 48% to 56%. So this 0.6 is not in there.
Okay, wait, where did the 0.48 to 0.56 come from?
What's that?
So where did that come from, the 0.48 to 0.56?
This is what we did last time. We can go ahead and review that. So remember that your formula here is your sample proportion, p hat, minus your z value, times the square root of p hat times 1 minus p hat divided by your sample size n. And it's the same thing on the other side. Except that the minus is replaced with a plus. And if you read that article or just looked at that one picture that I showed you, our p hat value there was 0.52, and our n value, if you read that article, is 600. So we had 0.52 minus the z critical value that comes from the z table, which is 1.96, times the square root of 0.52, and 1 minus 0.52 is 0.48, divided by the sample size of 600. And on the other side, we get the same thing, except change this to a plus, and then you'll get that interval that we had there. This is equal to 0.48 to 0.56. And they saw a couple of questions pop up. How do you get the p hat value? So this is the sample proportion. So I'm going to take, so in that situation, p hat is the sample proportion. So in that study that they did, that poll, they got a p hat value of 52%. So that means 312 out of the 600 surveyed said they would vote for Biden. So p hat is the 312 over 600, which gives us our 0.52. So that's how you're going to find it in real life. You're going to do some type of survey. All of the yeses you count up, that's your numerator, and your total sample size is the denominator. Let's see, was that the only question? Yeah, okay. And I got that number. Here's the sample size here that says 600. And they also have the margin of error. That's why I added and subtracted 0.4. You can see here's the p hat value from that sample. So you can read there's tons of polls like this right now that you can look at and actually use what you're learning in this class to help understand those. All right, we're going to go to lecture 25 and talk about hypothesis test for proportions. So when we talked about hypothesis tests for sample means, there were 3 different types. This two-tailed one we could do by computing a confidence interval like we just did, but these are a little bit different and we have to compute those differently. So we've got the left-tailed test that looks the same as before. It's left-tailed because in the alternative hypothesis, we have less than. The right-tailed test, which is right-tailed because we have greater than. Equals is always going to be in your null hypothesis. And your research question is always going to decide which one of these alternative hypotheses you'll use. For proportion, P is the symbol that we're going to use for population proportion, so you always need the P here when you're talking about that. So on the final exam, you'll have two choices. Should this be about mu or should this be about P? The steps are the same. So step 1, come up with your hypotheses. Step 2, decide on what your alpha value is, your probability of a type 1 error. On the exam and on homework, I will give this value to you. Step 3 is to check the assumptions. This is different, and it's different than the assumptions that we have when we compute the confidence interval. So we're going to let P sub 0 be the hypothesized value in the null hypothesis. So whatever this value is, we're going to give that the symbol P sub 0 right now. So H naught is P equals P sub 0. Here are the assumptions that we need to check. Number 1 is the same that we've seen over and over again. A simple random sample was taken. Number 2 is a little bit different than what we had for confidence intervals. We're going to do n times our hypothesized proportion has to be greater than or equal to 10, and n times 1 minus our hypothesized proportion has to be greater than or equal to 10. If both of these are true, then our sample size is large enough for the central limit theorem to apply, and that means our distribution of p hats is approximately normal. We're going to find a z critical value. When we did means, we talked about a t critical value, but for proportions, we're always going to use z values because of the fact that we don't have to estimate the population standard deviation. We'll write down the decision rule. A lot of people had problems with this on the test. I was asking something that was simple, but a lot of people skipped ahead and wrote down something that was more complicated, and I gave them credit anyways. I think I'll get rid of this in future exams. It's just confusing people. We'll collect a sample and compute the value of our test statistic. So that's our z-calc value. So z-calc, it's a little bit different again. We've got our sample proportion, p hat, minus our hypothesized proportion, p sub 0, and in the denominator, we have p sub 0 times 1 minus p sub 0 over sample size, and we're going to square root this entire quantity. So note that p sub 0, your hypothesized proportion, is used in the denominator, not p hat. This is because we assume that the null value for p is true until proven otherwise. So we're saying if h naught is true, what is the probability that we get a sample like ours? The next step is to decide whether to reject or fail to reject our hypothesis, and then write a conclusion that anyone can understand and state the significance level. So we're going to look at an article that was published about the proportions of LA residents who have had the coronavirus so far, and we're going to use the article to do a 8-step hypothesis test, and our hypothesis that we're investigating is the proportion of LA County residents who have had the coronavirus greater than 2% at the 5% significance level. A lot of students get confused because now there's multiple percents. This is the significance level. This is just our value of alpha. This is our hypothesized value of p. So I'm going to type this up in a Word document. So our research question is the proportion of LA County residents who have had coronavirus greater than 2%. first step is to write our hypotheses. So our null hypothesis is we're going to assume that this percent is 2% unless proven otherwise. So that's coming from this part here. And the alternative is we want to know, is it greater than this? Our significance level for the test is 5%. And we have to check our assumptions. So here's the article that I got this from. This is antibody testing. It suggests that the number of COVID-19 infections is greater than documented. And in here it says how they conducted the test. It's a drive-through testing here. And I think this is a blood test. I think they need a blood sample here. So the two questions that we need to answer is our sample size large enough to assume a normal distribution, and is this a simple random sample? One thing that I couldn't find in here, though, is the sample size. But they do say that there's this margin of error. This right here is a confidence interval. So we can determine the sample size from this confidence interval. So before we start, we got to figure out, well, what is the sample size based on this? This 4.1% is the middle, so we can calculate our margin of error based on that. So 4.1% is the middle, and it goes from 2.8 to 5.6. So the distance between 4.1 and 2.8, so we do 4.1 minus 2.8, and you get 1.3. That's a little weird because I expect this to be in the center, but it's not. It's a little skewed. So we are going to find the center of this interval. So before I can even begin, we got to do some detective work. We are going to determine sample size from the interval given. We're going to have to make an assumption that this is we're going to have to decide what the confidence level is here. So we are going to assume the confidence level is 95%. So we have this relationship that the margin of error is the width. I should say, yeah, it's the width divided by 2. So they said it was from 2.8 to 5.6. So we'll do 5.6 minus 2.8, and we get the width. And that is 2.8. So that means our margin of error is half of that, 1.4. So I gotta solve for n. Margin of error is equal to 1.96 times the square root. Oh, so this is going to be just like what we did. So we'll use that formula that we had. So we had the formula that n was equal to our z value squared times our p-value squared all over our margin of error squared. P hat is what's in the middle of this interval. I'm going to say that's 4.2. So if we put everything into this formula, we get that this is 1.96 squared times our p hat value z as a decimal 0.042 quantity squared divided by our margin of error as a decimal squared. And I get a weird sample size, like 35. So we'll just pretend this is 35. I think I did something wrong. There's only 5 more minutes left in class. I think I'm going to clean this example up and give you a new example next time because there's something weird going on here. Not quite sure what it is. Do you guys have any questions before we call it a day?
Where did the 1.96 come from?
The 1.96 comes from, let's go to the t-table and look at that. So 1.96 comes from, I don't like the z-table. Let's go to the t-table, and I'll go to the t-table that I gave you. If you use this t-table, it's set up so you can do confidence intervals. So we're doing a 95% confidence interval, or we're assuming that what they gave us there was a 95% confidence interval. So if I go all the way to the bottom, I get the z value. So if you look at this row here, it says z, and that's where you can get the z values for these confidence intervals. Other questions?
Thank you.
Sorry about the example. I'm not quite sure exactly what they did. All right, if you guys don't have any other questions, then I'll see you next time.
Would you mind going back to the
Thank you.
whiteboard, please? Yeah, so, okay. Well, I don't remember where was it, because I think it's underneath. It's below. Scroll down. Just wanted to know the 0.42 if it was the confidence interval, or what was that?
0.42.
I think this is the previous problem. Yeah. Yeah. So we just finished that problem with the poll. Yeah, I just wanted to know if the I don't remember what number was that one. If it was the sum of the oh my gosh, it was a 2.8 and a 1.2 or 1.4, and I wanted to know if that 4.2 that we found was the sum of those numbers.
Oh, okay. Yeah. I see what you're
Yeah.
saying. So
Yeah.
the paper gave us a confidence interval, but I'm not
Okay.
sure where they got it from because it doesn't say like what the sample size is or what the confidence level is.
Okay.
The confidence interval given in the article was 0.028 to 0.028 to 0.056. So to figure out the p-hat value,
I can't see this the screen. I just wanted to let you know real quick.
thanks.
Sure.
Here we go. Okay.
Yeah.
Confidence
There we
interval
go.
in the article was 0.028 to 0.056. To figure out the p-hat value, find the center. So to find the center, we add them together and divide by 2.
Got
Add
it.
endpoints together. And divide by 2. This gives 0.042.
Got it. Okay. Which in decimal, I mean hundreds is going to be a 4.2. Okay.
Yeah, so
percent.
in this article here, they say it's 4.1%. So that means like there's some sort of rounding error going on.
Wow. Okay. Okay. Yes, I just wanted to figure out because I didn't get that part. Okay.
I gotta figure out their sample size. It's bothering me that it wasn't in here.
That's an interesting article, actually.
If it's true, it means that the mortality rate is really small.
Hopefully, it's true. Otherwise, we're just going to believe the information that's not true.
Anything else?
No, that will be. Thank you very much.
Yep.
Have a good day.